In this lecture, we will be discussing about the numerical example of backpropagation algorithm. So if you remember in the previous lecture, we have discussed about the theoretical concept of the backpropagation algorithm, that is we have seen the different derivations. So here let us discuss the same backpropagation algorithm with the help of numerical example so that it would be more clear in understanding how actually the backpropagation algorithm is going to work out. So let us start. Let us consider a neural network with two inputs, two hidden neurons and two output neurons. So this is input 1 and this is input 2. This is hidden neuron 1 and this is hidden neuron 2, and this is output neuron 1 and output neuron 2. Additionally, the hidden neurons and the output neurons are also having the bias. Let us see the values of these inputs and weights. The input 1 is 0.05 and the input 2 is 0.10. And the weight W1, which is connecting the input 1 to the hidden neuron H1, is 0.15, and the weight W2, so this is the weight W2. This line from input node I2 to H1 is associated with a weight W2, which is 0.20, and this line from input node I1 to hidden neuron H2 is W3, which is given by 0.25, and this line from input node I2 to the hidden neuron H2 is given with the weight 4, 0.30. And in the same way, from H1 to O1, this is W5, which is 0.40, and from H1 to output neuron 2, the weight is W7, 0.50, and from H2 to output neuron 1, the weight is W6, 0.45, and from H2 to the output neuron 2 is W8, which is given by 0.55, and the desired output for the output neuron 1 is 0.01 and the desired output for the output neuron 2 is 0.99. So these are all the values of the inputs, weights and outputs we have assumed to work with the network initially. So now what is the goal of the backpropagation algorithm? So the goal is to optimize the weights so that the neural network can learn how to correctly map the arbitrary inputs to the outputs. And in the complete discussion of the backpropagation algorithm, we work with the inputs. Input 1 is equal to 0.05 and input 2 is equal to 0.10, and we want the neural network to give the output values which are equal to 0.01 and 0.99 for the output neuron 1 and output neuron 2 respectively. Okay, now let us start with the first step, the forward pass. So here we will see what the neural network currently predicts when the weights, biases and inputs are given. So to do this, we will feed these inputs forward into the network. So here we aim to find out the total net input to the each hidden layer neuron. That is, we wanted to find the total net input to the hidden layer neuron H1, and we want to find the net input to the hidden layer neuron H2. And to produce the output, we are going to use the logistic or sigmoid activation function at each and every hidden layer neuron, that is H1 and H2. And then we repeat the process with the output layer neurons also. Okay, let us now calculate the net input to the hidden neuron H1, which will be computing by weight 1 into input 1 plus this weight 2 into input 2 plus this fixed input 1 into the bias value. So that's what we have done here, W1 into I1 plus W2 into I2 plus B1 into 1. So we have placed the W values and I values, that is weight 1 is 0.15 and the input 1 is 0.05, weight 2 is 0.20 and the input 2 is 0.10 and 1 into the bias value B1 value is 0.35. So after calculating this, we got the net input for the hidden neuron H1 as 0.3775. So we simply pass this value, net input value of this hidden neuron H1 through the activation function, and then we will get the output. So The output of hidden neuron H1 is calculated as by using the logistic function formula 1 by 1 plus e power minus the net input of the hidden neuron H1. So this value gives us 0.593269992. So at this point we have found out the output value of this hidden neuron 1. So similarly we can also calculate the output value of this hidden neuron 2, and we get the value for the output value of hidden neuron 2 is 0.5968884378. So let us now calculate the net input for the output neuron O1. So what will be the net input for the output neuron O1? That is the output from H1 into the weight value, which is W5, plus the output value of H2 into the weight W6, plus the fixed input 1 into the bias value. So this is what we have done here, that is W5 into the output value of H1, because the output value of the hidden neuron will be the input to the output neuron 1, right? And next plus W6 into output value of hidden neuron H2 plus the second bias value, that is B2 into 1. So by putting all these values, we will be getting the net output value of the output neuron 1 is 1.105905905967. So now we pass this value through the activation function so that we could find out the output value of the output neuron 1. So the output value of the output neuron 1 is equal to 1 by 1 plus e power minus the input value to the output neuron 1, which is equal to 1 by 1 plus e power minus 1.105905905967, which is equal to 0.75136507. Similarly for the output neuron O2, so this is the output neuron O2. So if we follow the same process as we followed for the output neuron O1, the final output value of this output neuron O2 is equal to 0.7729288465. So till now we have found out the input value, that is the net input value to H1 and the output of H1, the net input value to H2 and the output of H2, and then we have found out the output value for this output layer neuron O1 and the output of the neuron O2 also. Okay. So our next step is to calculate the total error. So to calculate the total error, so first of all we have to calculate the error for each of the output neurons using the squared error function, and then we have to sum up all these squared errors to get the total error. So that is E total, that is the total error is given by E total is equal to summation of 1 by 2 into the target output or desired output minus the actual output square, that is the squared error function, right? If you remember when we were discussing about the derivation of the backpropagation algorithm, so we used the formula E of n is equal to 1 by 2 into Ej of n square, so which is nothing but the squared error. So here Ej means nothing but the desired output minus the actual output, right? So for this reason the total error will be calculated like this. Okay. So let us now calculate the error for the output neuron 1. Okay. So we already assumed that the target output or the desired output of the output neuron 1 as 0.01. So if you observe in this diagram, the assumed target output is 0.01 for the output neuron 1, and then we calculated the actual output given by the output neuron O1 in the previous step, right? So this is the actual output given by the output neuron 1, which is 0.75136507, right? So now what is the error at the output neuron 1? So E01 is equal to 1 by 2 into the desired value or the target value of the output neuron 1 minus the actual value we have got, that is squared error, okay, is equal to 1 by 2 into, so the target value we assumed is 0.01 and the actual value we have got is this one. So finally the error for output neuron 1 is given by 0.2748111083. So similarly for the error at output neuron 2, we are going to calculate in the same manner, that is E02 is equal to 1 by 2 into the target value or desired value of output neuron 2 minus the actual value we got. So by doing this calculation, we got the error at the output neuron 2 as 0.023560026. So now the total error is the error at the output neuron 1 plus the error at output neuron 2. So these are the values we have just now calculated. So the total error will be 0.298371109. So let us now step into the next step, which is nothing but the backward pass. So the goal of the backpropagation algorithm is to update each of the weights in the network so that the actual output of the neurons is closer to the target output or desired output. So thereby we minimize the error for the each output neuron. So if we minimize the error for each output neuron, we finally minimize the error for the entire network, right? So first of all, we will consider the output layer, that is we will try to update the weights, that is W5, W6, W7, W8 in the output layer, and then we go back from this output layer to again the hidden layer and we try to update the weights W1, W2, W3 and W4. So in this manner we update the weights in this layer first of all, that is W5, W6, W7 and W8, and then we go back to the hidden layer and we update the weights here, that is W1, W2, W3, W4. So finally our aim is to reduce the difference between the target output, that is the desired output, and the actual output produced by the output neurons. So let us now consider the output layer. We try to update the weight W5. So when we consider the weight W5, here we have to identify how much change in the weight W5 affects the total error, right? So that is dou E total by dou W5, so which is nothing but the gradient with respect to W5. So here we are checking how much change in this weight W5 is going to affect the total error. So this can be obtained by applying the chain rule, that is the change in the total energy with respect to the change in weight W5 is equal to the change in the total energy with respect to the output value of the output neuron 1 into the change in output neuron 1's value with respect to the change in the input value of the output neuron 1 into the change in the input of the output neuron 1 with respect to the change in the weight W5. So if you just refer to the chain rule when we have derived the backpropagation algorithm, it would be easy for you how we have got this particular formula. Okay, now first of all we have to calculate the change in the total energy with respect to the change in the output value of the output neuron 1. So let's calculate this first term. Okay, so we already know that the total energy, the total error energy is equal to the sum of the squares of errors, right? So half into the target value of the output neuron 1 minus the actual output we got whole square plus half into the target value or desired value of the output neuron 2 minus the actual output we have got at the output neuron 2 whole square. Now we are going to apply the partial derivative with respect to the output value of the output neuron 1. So now if we apply the partial derivative for this, what will be our derivation? So this for this one will be this half into, so if it is x square 2 into x power n minus 1, right? So this 2 into, so let us say if this is x power n minus 1 into, so for this one we are partially derivating this total error energy with respect to the output value of the output neuron 1. So here now we do not consider the output neuron 2's value, right? So for this reason this complete term will be becoming 0. Okay, so here we got 2 into 1 by 2 into target value of the output neuron 1 minus the actual value of the output neuron, and for this again the derivative is minus 1, right? So that is the reason we have got minus 1 here. So if you observe, for your convenience I have written here, let us say z is equal to 1 by 2 x square plus 1 by 2 y square. So now we are partially deriving, that is we are applying the partial derivative with respect to x. So it will be 1 by 2 into 2x into, again the derivative of x is 1, plus we are partially derivating this particular value with respect to x. For this reason this value will be constant and the derivative of this constant value is 0. So the same thing we have applied here. Okay, so now dou E total by dou output value of the output neuron 1 will be equal to minus of the target value at output neuron 1 minus the actual output we have got at output neuron. So minus of, so initially we assume that the desired value or the target value of the output neuron 1 is 0.01 minus the actual output value we have got. Previously we have calculated this value. Okay, so this will be equal to 0.74136,507. So till now we have calculated the value of this first term. So similarly we will be calculating the value of this second term, that is change in the output value of the output neuron 1 by change in the input value of the output neuron 1. So we already know that the output value of the output neuron 1 will be given by the activation function, which we are using the logistic function here, 1 by 1 plus e power minus the net input value of the output neuron 1. Okay, so now the derivative of this particular function will be giving us the output value of the output neuron 1 into 1 minus the output value of the output neuron 1. So these values we already know, that is the output value of the output neuron 1 we already know. So by applying these values we got a value called 0.186815602, that is we have calculated the second term. Now we have to calculate the third term, that is change in the net input value of the output neuron 1 with respect to the change in the weight 5. That is the net input value of the output neuron can be given by, so if you see here, the net input value of this output neuron can be given by the output value of the hidden neuron H1 into weight 5 plus the output value of the hidden neuron H2 into weight 6 plus again the fixed input value 1 into the bias value. So this is what we have written here. So now we are going to apply the partial derivative of the net input value of the output neuron 1 with respect to the change in the weight 5. So now if you do the partial derivative, what will be this value? So we are doing with respect to W5 value, so this will be 1 into this value plus, as we are doing with respect to W5, this will be constant, so it is 0, and this will also be constant and this will be 0. And what is the final output value? That is the final value of this particular derivative is equal to the output value of H1. So this output value of the neuron H1 we have already calculated above, right? So this will be our value of this one. So now we have calculated the three parts, this part, this part and this part. So finally putting them all together, so we are going to put this value and this value, we will be getting the value 0.082167041. Okay. So now the final value, that is the change in the total error energy with respect to the change in the weight 5 is given as minus of the target value of the output neuron 1 minus the actual value of the output neuron we got into the actual value of the output neuron 1 into 1 minus the actual value of the output neuron 1 into the actual value of the hidden neuron 1. So we can represent these values in the form of their own derivative values which we have calculated earlier, right? So this value can be represented as minus of the target value of the output neuron 1 minus the actual value of the output neuron 1 into, and this can be written as the actual value we have got at the output neuron 1 into 1 minus the actual value we have got as the output at output neuron 1 into, and this one can be written as the output value we have got at the hidden neuron 1. So for simplification we can write these two terms, that is we can replace these two terms with delta 0 1. Okay, so these two terms can now be written as follows: dou E total by dou net input of the output neuron 1 is equal to delta output neuron 1. So finally what will be this value? The change in the total error energy with respect to the change in weight 5 is equal to this value we have substituted with delta 0 1 into the output value of the hidden neuron H1. If you remember, while we are deriving the formula in the back propagation algorithm in our derivation, actually the change in the total error energy with respect to the change in the output value of the output neuron 1 will be given as follows. And this value we have given as -1 in our derivation. Okay, so finally this value completely can be replaced with the minus value of delta 01. So the actual representation of the change in total error energy with respect to the change in the weight W5 is given as minus delta output neuron 1 into the output of the hidden neuron 1. But we know that the correction of the weights, that is delta Wji of n, which is defined by delta Wji of n is equal to minus eta into dou E of n by dou Wji of n. So minus eta into, what is the value of this one? This one is minus delta at output neuron 1 into output value of the hidden neuron 1. So which will be given by delta Wji of n is equal to eta, the learning rate parameter, into delta the output neuron 1 into the output of the hidden layer neuron H1. So finally the change in the weight of W5. So now we wanted to update the weight of W5, right? So all we are doing till now is to update the value of W5 so that the error can be minimized, right? So let us assume the eta value to be 0.5. So the change in the weight W5 is now given by delta W5 is equal to eta into dou E total by dou W5, that is the change in the total error energy with respect to the change in weight W5. So we have already calculated this value as 0.082167041. So now this eta is the learning rate parameter. Let us assume that the eta value is 0.5. Then the final delta W5 value will be 0.5 into this value, which is, we got it as 0.0410835205. So now how can we calculate the updated weight of W5? So we represented the updated weight of W5 as W5 plus, so which is given by the updated weight of W5 is given by the previous or the old value of W5 minus the change in the weight 5 value just we have got now. Okay, so is equal to the original value of W5 is 0.4 minus the change in the W5 value we have got just now is 0.041, right? So we subtract this value from this value. So the final updated value will be 0.35891648. So the previous value of W5 is 0.40, right? But now the updated value has become as 0.35891648. So in similar manner, we can also update the weights of W6, W7 and W8. So after calculation, we got the updated weights of W6, W7 and W8 as follows. So what we have done till now? So till now we have calculated the updated weights of W5, W6, W7 and W8. That is, we have calculated the updates in these weights. Now the next step is we have to calculate the updates in these weights, that is W1, W2, W3 and W4. So finally after calculating the updation in these weights also, so then only we could be able to reduce the error between the desired output and the actual output we got. So we wanted to minimize the error, right? So to minimize the error only, we are now going to update the weights. So till now we have updated the weights up in this particular output layer. So now we are going to update the weights in the hidden layer. So these updations we will be discussing as a part of the next class. Thank you.